Bismillahirrahmanirrahim. Welcome back to VLSI design course after the midterm. So now we start with the another topic which will lead to delay in power consumption in CMOS circuits. So DC and transients for the MOS transistors and the circuits, particularly the inverter circuit. So this is the outline of presentation. Pass transistors, the DC response, logic levels and noise margins, transient response, RC delay models, delay estimation. Now some of the topics we have already covered, but they are here because these are the slides for the full chapter. So we talked about this and we talked about this. So we will go over quickly on these two, and we will discuss the others in some detail. Okay, so pass transistors. Now if you remember, we always used to say that the NMOS passes a weak one. This slide is the reason why it passes a weak one. So until now we have been using the source and it was grounded, okay? But what if the source is not grounded and for example we have VDD connected to the source? So this is our gate, source and drain. So what happens in that case? So VG is equal to VDD and a voltage at the source. So let me draw another circuit so that you can better understand. So for example, here we have our NMOS, this is our gate, and here we have our ground, and normally we have load capacitance here. So whatever thing we connect at the output, it has some internal capacitance. So this is our VG, this is our VS, this is our VD. So imagine that VG is equal to VDD. So we need a positive voltage for the transistor to turn on. So in this case the transistor is turned on and the current ID will start flowing, okay? So in fact it is something like this. Sorry, you can say that the capacitor is here, so the current start flowing. This is our ID and the capacitor starts to get charging. Now if you remember that there is a threshold voltage VT that the transistor has to overcome in order for it to be turned on. So until VG is, the gate voltage is less than threshold voltage, the transistor is off. When the gate voltage crosses threshold voltage, then the transistor turns on. So you can say that effectively at this point the voltage is VDD minus VT. So it will never be equal to VDD. This voltage will never be equal to VDD, because if it is greater than VDD, if it is greater than VDD minus VT, the transistor will turn off. So because of the threshold voltage drop here, this voltage is always less than VDD, and that's why we say that the NMOS passes a weak 1. It is not VDD, but it is VDD minus the threshold voltage. So that was the reason. And the same way a PMOS passes weak 0. Okay, so if you need both strong 1 and strong 0, we discussed that we need transmission gates. So again, here are two configuration. So the voltage at the source is always equal to, if this is the drain, it is always equal to VDD minus VTN. This N is for NMOS, and for PMOS the threshold voltage is represented by VTP. Okay, so if you have this circuit, then the voltage here is VDD minus VTN, and the voltage here is also VDD minus VTN, because it's always compared, or it is always with respect to the gate voltage. But if you have this circuit in which this is the drain and this is the Vs, but it is connected to the Vg of another transistor, in this case the voltage here is VDD minus VTN, and the voltage here is VDD minus 2 VTN. Okay, VDD minus 2 VTN. So in this case it is sequentially decreasing, incrementally decreasing. Okay, you see it's here and it's here. So you should never connect the pass transistors in this cascade manner. So cascading is not a better option. Okay, because the signal strength decreases with each cascading stage. Now, what is DC response? DC response is a response which does not change with time. So the response of a transistor circuit which does not change with time. So DC response is basically the Vn versus Vout for a gate. So for example, if we consider NOT gate, this is very familiar to you. A PMOS and an NMOS case in series, and the gates are shorted. So if we apply a Vn0, so it is an inverter, the Vout is VDD. If we apply a Vn VDD, the output is Vout is 0. But in between these two voltages, what is the behavior of transistor? What is the current? Okay, so it depends on the size of transistor and current. So in between, Vout depends on, so for this voltage Vout is this, for this voltage Vout is this, but what about the other configurations, other options? So it depends on the transistor size and the current. By size we mean the W, okay, which was the width of polysilicon. You remember that there was a L, which was the channel length, and there was a W, that was the width of polysilicon. Okay, so in this circuit we always have this IDSN is equal to IDSP. IDSN is the current flowing through the NMOS, IDSP is the current flowing to the PMOS, and you see the absolute value because the current is carried by holes and it has a negative sign. So we are talking about the absolute current. So let's see, one solution is to write equations, but we can do it graphically. So let's see what is the DC response. So the transistor operates basically in three regions, which are cutoff, linear, and saturation. And you already know these three regions from the material before midterm. We have discussed in great details the transistor characteristic curve, and we have studied the square law model and the velocity saturated models. Okay, so you know the cutoff region, the linear region, and the saturation region. So when the for an NMOS, when the gate to source voltage, okay, so this is our gate, this is our source, drain, gate, source, drain. Okay, so the gate to source voltage, if this voltage is less than the threshold voltage, the transistor is off, it is in the cutoff region. Okay, when the gate to source voltage crosses the threshold voltage, the transistor turns on. Okay, and so if you remember the transistor curve, it was something like this. On this axis we had VDS, on this one we have ID, and then we had a family of curves for VGS1, VGS 2, VGS 3, VGS 4. So we have this family of curves. Okay, so where was the linear region? The linear region was on the left hand side of this point where the transistor saturates. Okay, so for that region, the VDS, this point was VGS minus VTN. Okay, so when when VDS is less than this point, you are in the linear region. So for linear region, we have two conditions: the VGS n should be greater than VT, and the VDSN should be less than VGSN minus VTN. And in the saturation region, again VGS should be greater than threshold, because this is what is required for transistor to be on, and the VDS is now greater than this value. Okay, before it was less, now it is greater than this value. So what about input and output? Because the VN is connected to VGSN. Okay, so we have this and we have this. So basically all the above equation can be written in terms of the input and output. So this equation can be written like this. This equation can be written like this, this, and this. Okay, so these are just equivalent, because you are just replacing the VGS with VN and VDS with your V out. The same goes for PMOS, so it is the opposite of NMOS, and you can work out this table. Now if we plot the input output characteristic of NMOS, so this is our NMOS characteristic and this is our PMOS characteristic. Remember that I told you that the current value is negative, and that's why all the currents are negative for the PMOS. So you get this kind of curve. The betas are basically the gains of the NMOS. Dn is for NMOS and dp is for PMOS. So this is basically comes from another model that is called Shockley model that we haven't covered. This is a very old model. What we have covered in our material, they were the latest models for describing the IV characteristic. Shockley model is a very old model, but the book has Shockley model. So it is basically the gain of transistor in Shockley model. So what we can do is, if we plot the absolute of the PMOS current, we will get a curve like this. The blue ones are for PMOS and the green ones are for NMOS. So nothing special, just the absolute values, and we have flipped the curve in the first quarter of the Cartesian coordinate. Now what is happening? How can we describe the DC characteristic? This is done by a method that is called load line analysis. For a given Vn, we plot IDSN, IDSP versus Vout. Vout must be where current are equal. So for example, let's consider this point when Vn is 0. So when Vn is 0, what happens? Remember our circuit. We have a PMOS, we have NMOS. This is our Vn, this is our Vout, VDD, and our ground. So what happens when Vn is 0? The NMOS is off and the PMOS is on. Okay, when the PMOS is on, Vout is equal to VDD, so we get this red line on the output, because here is our output. Okay, what happens when Vn is 0.2 VDD? So what happens at that point when it is not equal to VDD, but it is, let's say, 20% of the VDD? Okay, so in that case, okay, so just note that I'm coming to the case of Vn is equal to 0 again, and just note that the current is blue, which means this current is the current of PMOS, and because when this is 0, the PMOS is on, so we have a current flowing here. That's why the current is due to the blue line. It is due to the PMOS, and the output voltage is equal to VDD. Now let's come to the second case, in which the Vn is equal to 0.2. It is basically 20% of the VDD. What happens in that case? So you see there is a very small curve here for NMOS, which means that the NMOS is in cutoff region. So the 20% of VDD is so low that the NMOS is in the cutoff region, and you have no current, and the output is almost at that point, the same point. Okay, now let's see what happens when the voltage increases at the input to 40% of VDD. So you see that the NMOS curve has now risen up, and these 2 points intersect. These 2 currents intersect at this point. Okay, so wherever they intersect, the output voltage will be equal to that, because this is the solution. You cannot have different current. You always has this condition that IDSN is equal to IDSP. This is what is meant by this point. Okay, so we are solving it graphically. So you extend it on the x-axis, and the VDD is now slightly less than VDD. Vout is slightly less than VDD. Okay. Now we increase the voltage further, and when you increase it further, you see you are entering into the other voltage level, to the logic 1 level. So this means that we have logic 1 at the input, which means that now this will be off and this will be on. Okay, so now you are entering at that to that region, and you see now that both the curves cross here. So you have the output voltage which is very close to 0. What happens if the voltage is 80% of the VDD? Now PMOS goes into cutoff. Okay, you see this curve. So the PMOS is going into cutoff region, and that's why you have the output voltage that is 0 volts. Okay, so or very close to 0 volts, and when it is equal to VDD, you will have the output voltage equal to 0. So when you plot this, all these points, okay, if we plot the VN versus V out, okay, we get a curve like the red one here. So this is called the DC transfer curve. Okay, this is called the DC transfer curve. You have all these points A, B, C, D, which represents if the transistor NMOS is in the cutoff region and PMOS is in the saturation region, and so vice versa. So all these points you can now analyze if the PMOS is in cutoff, or if the NMOS is in the cutoff or saturation. You see, between these two we have a very steep slope, and it occurs at this voltage VDD divided by 2. So it's you say you want to have such a high slope, but it depends on the gain of transistors used in the inverter. So it may not, ideally you want that this line should be at VDD divided by 2, but due to the differences in gain and all these things, this may not be at VDD divided by 2. Such gates are called skewed gates. Okay, but for our discussion, let's imagine that we have these perfect transistors which have the gain such that we always get it at VDD divided by 2. And again, just I told you that if you consider this region, the point A, which means the output is high, so the high means that the pull-up network is active. So this is pull-down network. Okay, NMOS is pull-down network, and this is pull-up network. So the NMOS is in the cutoff and PMOS is in linear region. Okay, because the input voltage is very near to 0. Okay, point B means the NMOS is in the saturation and the PMOS is in the linear region. Remember that whenever you have this output is 1, so the output 1 is coming from the PMOS. Okay, so C saturation, linear cutoff. Okay, so this is the slide where I talk about the skewed gates. So when the betas are not equal, then the switching point will not be at VDD divided by 2. So this is some detail. Okay, this is the noise margin, and I told you that we have discussed some of the topics. So we went through in great detail on the noise margin before midterms. So here also we have the voltage levels. So you see the VIL, VIH, VOL, VOH, all these things for transistors. So here they are given. Okay, so this was the DC response. Now let's come to the transient response. So DC analysis tell us about V out if Vn is constant. Transient analysis, we have this time parameter there. So the quantities are time varying, and you remember that whenever you have time varying things, you have to solve linear differential equations for circuits, or Laplace transform if you want to deal with it algebraically. So without going into the details of how this works, because we haven't discussed the Shockley model, so without going into the detail, the transient response of the inverter is like this. If this is the blue is our input, so it is 0 on this side, and then when the time is greater than t0, it switches to a 1. Okay, so this is our input. Now what happens on our output side is that it is 1 when the input is 0, because this is an inverter, and when it switches to 1, the output drops slowly. Okay, the output drops slowly to 0, not directly. And this is a very important characteristic that determines our delay. So if you look carefully, basically this kind of curve you have studied in circuit for the capacitors. This is the RC discharge of a capacitor. So the RC discharge and RC charge of a capacitor are very important to determine the delay of a CMOS circuit. Okay, and this comes from the transient response. In this case, the particular transient response we are talking about is the step response. So this is a unit step response. Now we come to the formal parameters that are used in VLSI design for measuring delay. So the first one is TPD. TPD stands for propagation delay, and there is an R, small r, which means rising propagation delay. Okay, so it is from input to rising output crossing VDD by 2. So imagine the curves of our inverter. The first one is the curve of Vn, and the second curve is the curve of Vout. So when the definition of TPR, so let's first consider the definition of TPR, okay, rising propagation delay. So when your input is going below 50%, so our input is going down 50%. 50% is this 0.5. So the total swing is 1 volt. So 0.5 is our 50%. When the output reaches 50%, which is again this point, so the time from here to here is called TPR, rising propagation delay. Okay. Similarly, the other is falling propagation delay. So when the output is falling, then we have average propagation delay. This is called TPD. So it is basically TPDR plus TPDF divided by 2. Then we have the rise time from output crossing 0.2 VDD to output reaching 0.8. So this point is the point when the output crosses 0.2, and this is the point when it reaches 0.8. So in between this time is our rise time. Similarly, the fall time is from the 80% of VDD to 20% of VDD. Okay. Then we have another one which is called contamination delay. So for contamination delay, it is basically, sometimes it is called min delay, and the TPD is called max delay. Or let me give you another definition, that is, it is the amount of time for which your output is corresponding to previous input. So imagine that the input is 0. So you have this inverter, the input is 0. So at that point the output should be 1. Let's say that this was at t is equal to 0. At t is equal to 0.5, what happened, that Vn is 1, okay, but Vout is still 1, okay, because this change in input has not affected the output. So that amount of time is called contamination delay, the amount of time for which your output is corresponding to your previous input. So this output is corresponding to this previous input, not the current input. That is called contamination delay. So rising contamination delay, from input to rising output crossing VDD to falling contamination delay, from input to falling VDD 2, and average contamination delay is CD R plus CDF divided by 2. This is basically, sorry, this is not PD, this is TCD. Okay. Let me explain it a bit further, although it's not here. So to convey the concept of the TPD and TCD, let's say we have here is our VN and here is our Vout. So let's say, let me change the color. Let's say that our input is 0 1 0 1. Okay, now what happens at our output is that it is 1 corresponding to this. Then at this point the output changes from the input changes from 0 to 1. See, so the output has to go from 1 to 0. But as I told you, that this change will be very, very slow. Okay, let me draw this more widely. So here, and let's say it goes down here. Okay, so again switch to green, and then you see it becomes 0. So now we can see that there is an amount of time which is this one. Okay, for this time the output is the output is old, so it is the contamination delay. Okay, and then from here to here, you see this whole time is called TPD. This is the amount of time that is required for the output to get effect. And this from here to here is basically the RC discharge. So I can say that TPD is basically the contamination delay plus TRC. Okay, time for the capacitor to discharge. Now one way to get the accurate value of the delay of our inverter is to use a software program like SPICE. One way is to solve differential equation, the other way is to solve to simulate using SPICE, and then you can measure from SPICE the TPD. Both these methods are hard. What we want is we want to quickly estimate the delay. So we want to estimate delay. It may not be as accurate as simulation with SPICE, but it will be good for a quick analysis of CMOS circuits. So what we want is a delay model, and the delay model is called RC delay model, where C is the total capacitance on the output node and R is the effective resistance. So TPD is basically the RC time constant. Remember that I wrote TPD is equal to TCD plus TRC. Okay, but this is very, very small. TCD is very small compared to TPD, so we can neglect it and we can say TPD is equal to RC, where R is our effective resistance and C is the total capacitance at the output load node. Now let's see what this means. So again, there is the description of Shockley model, which we haven't discussed, but we don't need the details of Shockley model. What we want is the model for transistor. So let's move directly to the RC delay model. So let's focus on this slide. We use an equivalent circuit for a MOS transistor in which we have ideal switch plus capacitance plus on resistance. Okay, so for unit in MOS, so what we mean by unit, it is the minimum size, okay, that you can prepare in a certain technology. For example, by technology I mean, let's say we are talking about L of 32 nanometer. So what is the smallest NMOS that we can manufacture in 32 nanometer? That is called a unit NMOS. Similarly, what is the smallest PMOS that we can manufacture in 32 nanometer? That is called a unit PMOS. Now remember that a unit NMOS has a resistance R and a capacitance C, but a unit PMOS has a resistance 2R and a capacitance C. Why? Because the reason is that the electrons move fast compared to holes. So in NMOS, the majority carriers are electrons, so they move fast. In PMOS, the majority carriers are holes, so they move slowly. Okay, and the slow movement is modeled as a higher resistance. And always remember that the capacitance is proportional to the width of polysilicon or the width of transistor. So and again, resistance is inversely proportional to the width. Why inversely proportional? Because if you reduce if you increase the width, the electrons, the charge per unit time will increase. Okay, the current will increase, which will mean the resistance will decrease. So increasing width decreases the resistance. Increasing width, so ID is directly proportional to width, but R is inversely proportional to width, and similarly capacitance is directly proportional to C is directly proportional to width. Okay, so let's come to our RC model. So for our NMOS, we have this K. K is a constant that represents the how much you are above the minimum size. So I told you that the minimum size is the smallest NMOS or smallest PMOS you can manufacture in our technology. So K represents, if K is 1, it means we are talking about the unit NMOS. If K is 2, we are talking about an NMOS that is twice as large as the unit NMOS. So for that, NMOS is modeled by an ideal switch. So this is our switch. Then at the gate we have a capacitance that is CG, K times CG. We have a capacitance at the source, we have a capacitance at the drain, and we have an on resistance that is R by K. Similarly, for PMOS, we have this circuit. Again, you see that we have the drain, the source, and the gate capacitance, and you see here is 2R by K. The resistance is twice as high as the NMOS case. So this is our RC delay model. Okay, so this slide gives you the typical values for different capacitors. So for example, when the gate width W is 0.6 micrometer, the CG, CS, CD is 2 femtofarad per micrometer of the gate width, and for 65 nanometer it is 1 femtofarad per micrometer in 65 nanometer technology. Okay. Similarly, resistance, we have this, so you can read these numbers. They are okay. So let's come to solving the delay problem. So we are given this circuit. This circuit is, what is the circuit? These are two inverters. Okay, and why we have this 2 and this 1? So as we discussed that the effective resistance of NMOS is twice the effective resistance of NMOS. If we want to connect PMOS and NMOS in a series connection, and we want the same current to flow, if we want the same current strength from PMOS, we have to increase the width. Remember that ID was directly proportional to the width. So this 2 is our width, which means that if we want that the PMOS should pass the same current as the NMOS, the size of PMOS should be twice the size of NMOS. Okay, this is a very, very important concept that will be repeatedly used throughout the delay calculation. Okay, so the same goes for the second inverter, and we can for each transistor we have the model, so we can replace it with our model. So you see, for this transistor we have this one, this is NMOS. Okay, and see here is our output. Okay, what is meant by fan out of 1? By fan out we means how many things are connected to the output. So for example, if this two inverters are connected, we say the fan out of, for example, if this is A, this is B, we say the fan out of A is 1. But imagine that if we have this circuit and this is our A, we say that the fan out of A is 3. Okay, so this is what is meant by fan out. So you see, at this point, if we are looking into the second NOT gate, our circuit will only see the gate capacitance. So this is basically the gate capacitance of PMOS, and this is the gate capacitance of NMOS. So we are seeing this. Okay, and this is our PMOS model, and this is our NMOS RC model. Okay, you see the gates are why this is open and why this is closed, because this configuration is for A is equal to 1. When A is equal to 1, what happens is that our NMOS closes and our PMOS, this is our PMOS, this is open, and our NMOS is closed. So that's the equivalent circuit when our input is 1. So we can draw the equivalent circuit. Okay, let me remove this. It cannot be removed. Okay, so we have finally this one. Okay, this is the case when A is equal to, when the input is equal to 1. So this one was open, this one was closed. Okay, and we have all these capacitances coming from, this is coming from the RC model of PMOS, and this whole circuit is coming from the RC model of NMOS, and this is basically our fan out. So when we are looking into our second inverter, this is what our current sees: one gate capacitance of PMOS and gate capacitance of NMOS. So if we draw the equivalent circuit, because this one is open, so the equivalent circuit is something like this. We have an R, and this is our ground, and we have C. So you see, this is our VDD. Okay, so if you look closely, basically all these capacitors are in parallel. Why I say in parallel? Because this is our R and this is our capacitor going to the ground, I can draw this point where we have a capacitor, then we have a battery which is going to ground. Then I can draw this one, the capacitor. So this is 2C, this is C, this is C, and this is 2C. Okay, so all of them are in parallel, and you know that when capacitors are in parallel you have to add them. So our delay is 6 RC. So you see, we can very easily estimate the delay from the RC model. Just consider an input configuration. For example, I consider an input configuration of 1. Okay, you can consider an input configuration of 0, but maybe the input for the input configuration of 0 you make it a different delay. So you always have to consider the one which is maximum, which is the worst case. Okay, so you have to remember, this is very important point, that why not for a is equal to 0, we can calculate it, but if we calculate for a is equal to 0 and it is less than for a is equal to 1, then the delay will be the greatest one, not the smallest one. It is always for the worst case. So here we have a graph. So the green one is the curve for the Shockley model, then we have the SPICE, and then we have the curve for the RC model. So the curve for RC model is not 100% accurate, but it's acceptable. Okay, so let's stop here.